We were just discussing Armaun's future career plans, and he made a bold statement.
Machine learning is like building IKEA furniture.
You heard it here, folks. Machine learning is like building IKEA furniture. You can get a job easy. Right?
I think it's in that, like, I meant to, when there's a bunch of, like, stuff out there already, and you just have to, like,
Copy it.
connect them together.
Copy it.
I don't think it's, like, copying. Like,
Don't you just use an API?
yeah, basically. So it's, yeah.
So it's directly...
Yeah, like you call it, I guess. I guess you can say it's copying, but not really.
Okay.
It's like ethical copying.
Okay. So it's just using other people's stuff.
Yeah.
Okay.
And, like, you don't really need to know how it works. It's just a black box.
The answer is linear algebra.
Yeah. I think
I heard it wasn't, actually. Someone else told me it wasn't.
What, linear algebra?
Yeah.
It is.
Machine learning is all linear algebra?
It is.
Okay.
Well, it's like, if you want to do machine learning theory, that's different.
Oh, what's the theory?
Like how it works. Like, there is no theory.
There is no theory.
Because, like, that's like, so, like, linear algebra explains, like, how, like everything works, but, like, it doesn't explain, like, why some things work better than others. So, like, an overall theory, like, for example, like, people don't know, like, why, like with a neural network you can only have, like, 3 layers, and, like, that can solve anything, but, like enough hidden variables, but then somehow if you put more layers it makes it better. But, like, there's no, like, I don't know, there's no, like, theory, like, that explains any of it, or, like, what is, it's like a lot of it is just heuristic. So yeah, and that linear algebra can't explain that, really, or maybe it can, maybe we don't know it yet.
So how does machine learning work?
Well, there's many types of machine learning. There's, like, supervised, unsupervised, and, like, I think those are maybe, like, the 2 big distinctions. Like, but most of it is unsupervised, or most of what I have done is unsupervised, where it's like you get a bunch.
Make a script.
I know, you get a bunch of data and you don't know the groups in it, or you don't know like different structures, and you try having the computer identify them. And then
how does it do it?
It like tries, like, decomposing it. You treat the data as a matrix, and you try basically performing something kind of like an eigenvalue decomposition on it. And then each eigenvector, I guess this is, like, more of a simplified version, but, like, the eigenvectors kind of represent important structures. But you can do other stuff. Like, you can even find, like, if it's, like, time series, you can even find, like, what is required to go, like, in between 2 data points, like, from the first time. Like, if you have data in a matrix, so it's like x1, x2 is each, like, vector, like, until xn, and then you want to find some transformation that takes xn to xn plus 1, you can find that matrix.
Induction.
And then when you find that matrix, you can also decompose that one.
So why are the eigenvectors important?
Oh, because it's like a minimization, kind of just like, it's just like linear regression, but, like you can think of it in many ways. Like, if you were to, like, if you kind of do it in your head already, it's like if you were to, like, hold, like, I think many people give an example of, like, a tea kettle. If you hold a tea kettle and then you want to find the angle that best represents, like, the tea kettle, you would kind of, like, perform an eigenvalue decomposition in your head, and then find, like, the best bases to hold the kettle in, so you can see, like, the most of it.
So you're saying
it's like
the eigenvector basis is, like, the diagonal one?
Yeah,
so
it's like
you want to do that?
Yeah, the basis is the one that, and also, like, once you find the basis, you can find, like, how each of them, like, superimpose onto each other. Like, basically you can add them together, and then they can form, like, like, you can have, like, a time series. Like, you can have, like, their coefficients are dependent on time, and when you add them together, then it leads to all the structures that are in your data. It's just, like,
Isn't that very complicated?
No, it's not that bad. And, like, also another thing that eigenvalues provide you is that, like, the singular, like, or, like, the eigenvalues usually are not all, like, the same.
Yeah.
They have, like, usually a decreasing magnitude that's, like, almost exponential. Like, where it's, like, the first one's, like, 10 to the 4, the next one's 10 to the 2, and maybe the next one's also 10 to the 2, but then after that it's all like really close to 0. So then that means you can cut off the data and you only have to care about 3 of the eigenvalues, and you don't have to care about the other ones, and you can usually just label them as noise.
That sounds like very complicated.
It's not that bad.
What do you mean? The
Like-
theory sounds ridiculously complicated.
Like, no, it's like, I'm pretty sure you can get, like,
What?
if I wrote it on paper.
You just like pretend everything is a matrix, and then you just find the eigenvectors. And
Well,
why would
it's
that
actually-
why would that be meaningful?
Well, it's actually like, you can prove it like by, if you
How?
basically like get a vector, and then you want, okay, so you get a vector, and then you want to find what, like let's imagine you had like a 2-dimensional plot,
Okay.
and then you had data scattered on the 2-dimensional plot.
So
like,
our data is vectors. Is that what we're saying?
Sure, I guess you can imagine it like that.
Okay.
Yeah, but it's like scattered in almost like a line.
Okay.
It's kind of like those like linear regression line.
Wait,
like,
so what is the
scattered.
goal even of machine learning?
Like,
What is it supposed to do?
Well, that's like, this is one very specific application.
Okay.
It's called like principal component analysis.
Okay.
But like, this one helps find like the structures of the data. So it's like
Data structures.
yeah. So it's basically, it basically like helps you find like how you can best split the data. Like so it's like once
I see.
once you have this like scatter plot, you're going to find the vector that maximizes the projection of every vector, and that turns out to be the eigenvalue. If you do like the minimization problem, and then that vector would be the linear regression line straight through that scatter plot.
Yeah.
And then you would perform this linear regression again, but have the restriction that the next eigenvector be orthogonal to the eigenvector that you already have. So it's going to be like one line that goes through scatter points and one line that's orthogonal to it. And like those 2 points individually describe all the data. Like with those 2 coordinates, you can basically describe all the data points, right?
Yes.
But if you were to remove the one that's orthogonal, then it's still fine. You can pretty much like almost exactly approximate the line by itself. I don't know, I have to draw it on paper.
What is the purpose of the smaller one?
Like the smaller one is just like the complete eigenvector decomposition. So because it's 2 dimensions, there's 2 eigenvectors. But the second one is not really that important, and that's why we can cut it off as noise. And that is usually what noise is, right? It's like the deviation away from like the linear line.
So where's the part where you split stuff up?
So now, if you were to deal with more higher dimensional data, for example, if you have a bunch of images of birds, and then so you turn all the images into vectors,
Okay.
and then you perform this decomposition, then you're going to get a bunch of eigenvectors out because it's like million dimensions, and then
Okay.
and then it's like, but then the first few eigenvectors would probably represent something that looked like the bird.
Okay.
Or like some parts of like the background that are significant.
And then what do you do with that?
Like those are like, okay, if you were to do it with like some like physics example, like for example fluid flow, those structures would represent important structures in your flow that you need to keep track of. And like what's important in physics is that once you have these structures, you know that every new structure that's produced is just a combination of these structures, because it's just a linear combination of the eigenvectors. Because anything in that space, like the eigens like space, is just a linear combination of the eigenvectors.
Yeah.
So you know that you can basically get everything for those eigenvectors. And that's important in physics because now you can basically break down everything into its structure no matter how complicated it is. That's like one application. Then there's like other stuff like neural networks. Neural networks is just like basically nonlinear regression, basically. You can think of it that way. It's like,
oh, sure.
You wanna
With
do
higher
it-
order terms or something?
yeah, it's like,
Okay.
yeah, it's like so nonlinear. Like what neural networks does is basically you like give a linear input, like some input that's meaningful to you, and then it passes through a bunch of nonlinear stuff that you can tweak, and then you get an output, and then you keep tweaking these nonlinear stuff until you get some like output that has low error, and then you say that you have a model that predicts the stuff. And it doesn't have to be a straight line. It could be nonlinear because these are nonlinear components inside. And that's why people talk about layers, because the more layers you add, the more nonlinear things you're like hitting your original data with. So yeah.
That's kind of complicated
No, it's not that bad.
because it's like it's quite non-trivial to say that the important things are the eigenvectors.
Oh, wait, for this case, the eigenvectors are not important. For this
Cool.
case, you treat the weights of the neural network as a matrix, and then you can do you don't do decompositions of the weights, but you can adjust the weights in using like the gradient of the error to like it's just like a bunch of clever linear algebra to find a way to like fix the weights.
But in your earlier,
Yeah.
the previous method, you said it's through eigenvectors.
Yeah. Oh, it's not actually eigenvectors, because in reality, it's like you can't decompose a non-square matrix.
What do you mean? Everything's invertible.
But it's like, so your data, it's like if you have a bunch of pictures of birds, that means that if you want to invert that picture, you would have to take a certain number of pictures of birds to invert it. And that's not like realistic. No one's gonna have like millions of pictures of birds except
Sergey.
So it's like, what you do is like something else called singular value decomposition. Yeah.
Disgusting.
And you can basically treat the right and left eigenvectors, and like there's a lot of theory about what they mean. Most people call like half of them like the spatial eigenvectors, and the other ones the temporal eigenvectors.
Okay.
The spatial ones represent like for example, the pictures of birds represent like birds, like actual spatial things. But then like the temporal ones like give you like the time series, like how like I guess birds are not a good example because you're not taking it in a time series, but like if you have physics data that was taken like back to back over time, then these temporal eigenvectors would give you like data about like how these different structures appear over time. Like for example, like if you're doing weather data, you would see like there's a peak during winter of a certain type of pressure cycle, like that appeared in your eigenvector or something.
And how do you prove that?
You look at the coefficients and you see that at that point, like at a certain time range, it is like the highest, like has highest coefficient, so it has the most effect on the. Like,
So what? I mean, how do you know that the eigenvectors are like all that, you know?
yeah, well, that's a good question, and that's like
how
that's
that's
like one of the,
extremely non-trivial.
yeah, that's like the biggest question that people have.
Yeah.
Do these actually represent physical things?
Isn't this all
Or
observational?
are they just mathematics? Yeah, or is it just like some mathematical thing? That's a big unknown question that no one can answer, and that's
So isn't that quite complicated?
like I said before, like we don't know the theory of it.
Yeah.
We know that it works.
Isn't this garbage?
Sometimes it works, and
Isn't
sometimes
this-
it's horrible.
Yeah, this is terrible, isn't it?
Well, like sometimes it works really well.
Yeah.
Like it does stuff like we couldn't have ever done.
And how did anyone come up with this? They just like, are they monkeys?
Well, this one, like I think it came after singular value decomposition.
And they're just
Probably. Actually, I think it was some application of bio. Like I'm not joking. I think
like I'm not
there's a
joking.
guy
yeah.
named Fisher. He came up.
Bobby
he was,
Fischer.
I don't know. He was doing stuff with. He's
Okay.
doing stuff with like detecting like some like algae populations in the lake,
Mhm.
and then he tried splitting up the data because it wasn't split up, and then he came up with like one method that does this. He came up with one method that splits. It was like a simpler method, and then that got expanded on. But I think also a lot of this was not. So the mathematics was made a lot earlier, but then the applications came later. And actually, most of the time, like biologists rediscovered a lot of the math, and then
That's funny.
and after that, like it got like yeah,
So it was an accident.
not really. Because I think Fisher actually meant to do what he did.
Okay. I still have yet to hear like a real reason.
Of what?
Why? What makes eigenvectors so fundamental?
Yeah, that's a good question, and that's like no one knows the answer, and people get upset at each other for it.
Yeah,
Like,
I'm upset at you.
No, there was this like my mentor, like during high school, like he had this like the reason I think I originally started the project was like because there was there was this he saw this debate going on between people and he wanted to know whether they represent physical things, and then
What do you think?
yeah I don't know I don't think it's physical. Sometimes it messes up completely, but I think it's mathematical. It's just like optimal, like, but it doesn't mean it's physical, but sometimes it is. And yeah, and there's not really a good way to judge like how physical something is because it's just kind of like
numbers.
It's kind of like an ink blot test. Like you see the eigenvectors and you're like, oh, this definitely represents a structure because that's what I want to see. But then it doesn't have to. Yeah.
Yeah.
What about like the birds example?
Yeah.
What would the eigenvectors represent?
Oh, yeah, they probably wouldn't represent birds. I just said birds to make it simpler. But like, it would probably represent like tree branches or something,
Okay.
or like parts of a bird. Like,
Okay.
but it would not look that good.
So how does like photo identification work?
Oh, photo identification is very similar, like, but so for that one you have to go through a bunch of like processing, like basically a bunch of filters,
What?
Ground creeper.
Okay, resume.
like a bunch of filters to remove like stuff that can distract the algorithm, like the background,
Yeah.
shade, all that stuff, and then you
Okay.
extract out the bird, and then once you get the bird, you could do a like neural network algorithm. That usually is probably what they do, but if you want to go back to like, if you want to try using like what we talked about now, one thing you can do is like you can have a bunch of data and then project your image onto like a vector that represents like that bird.
And then whichever one's closest is...
Yeah, that's like a simple way to do it, but I'm pretty sure they have much more robust methods, like neural networks. Neural networks are good at identification.
So what you're saying is that the theory is very complicated, but the application is
I don't think
simple?
I don't think applications are simple, but I think like theory is not even solved.
Yeah.
So yeah, it's complicated, I guess.
Yeah.
Yeah.
I mean, what's like... The application is like whatever, you know?
Yeah, it's like everything.
But the theory... No. The theory is like, you understand fundamental things. Do you think so?
Yeah, I think so.
I mean, honestly, you're just like crunching random numbers. It's like, whatever. Cool, we got something nice.
But like sometimes it like leads to like it like speeds up stuff. Like this summer, like we were able to speed up simulations using machine learning.
Okay.
So it does like no one ever looked at those eigenfunctions or like eigenvalues or eigenvectors, and no one cared whether they're physical, but they helped in like making it faster. So
Sure. So is the meaning of life eigenvectors, do you think?
no.
No? I mean, that's kind of what your method just said. Hi.
You're fast.
Yeah. I wonder where you guys actually were looking
We cut through.
You do an engineering quad?
So we went through like the back of the main quad, like behind the church.
Oh yeah, I did it. And I was, have good Thanksgiving. See ya.
Intriguing. Wait, but you totally just told me the meaning of life is eigenvectors, right?
I didn't say the meaning of life.
Well, like... the building blocks of life. You know? The world is all about eigenvectors. Allegedly.
I don't think the world is like, or like the universe.
What do you mean? You just said everything? Well, I mean, everything you
So,
can
like, I
decompose
think, yeah,
into
just
eigenvector-ish
because
kind of thing,
You can
right?
decompose everything into numbers too. So it's like
Okay. So are numbers the world?
I guess.
But apparently eigenvectors have some special meaning.
Yeah, maybe. I said I don't know. Maybe they do.
Do they?
I'm not sure. Okay.
Hi.
Hey.
swooping in like a bird.